name's Susanna Green, and I'm very grateful and thankful for the British Computing Society for having me. And I'd also like to say a huge thank you for you joining us and taking an hour out of your time in the evening to be with me and explore the question, are machines the next Einstein? So in this talk, I'm going to give you a brief introduction to machine learning. And yes, my name is Susanna Green. I'm actually an astrophysicist, and that is my background. I'm currently researching how machine learning can be applied to the gravitational wave data analysis pipeline. And I'm part of the Institute of Cosmology and Gravitation in Portsmouth. So I'll go into briefly what I'm researching in machine learning later in my talk. But for now, we're going to give a brief overview of what machine learning is. So why is an astrophysicist doing a machine learning talk? I can hear you all asking this. Well, the reason is because my day-to-day life is actually oscillating between a software engineer, a machine learning engineer, and a data scientist. Plus, I also help out with a YouTube channel, which again, I'll link in the description, where we're trying to showcase that anyone can do physics. But for this talk, I'm going to be focusing on one of these hats, which is my machine learning engineering hat. So before we get into what is and how machines learn and think, let's take a step back and let's look at how we as humans think and learn. So did you know the average person has about 6,200 thoughts per day, according to psychologists at Queen's University? And I would love you to choose one of the three following options. So again, if you can either think about this or I've got the chat on my screen, so put this in the chat as well. A, if you have more thoughts than this per day. B, you have about this many thoughts per day. And C, you have very few thoughts per day. So yeah, please, as I said, if you want to get involved, there will be times when I do ask for audience participation, but if you don't want to, that's also fine. But yeah, for me personally, I think I would answer A, because I definitely have more thoughts than this per day. And in this question, I've got you to answer and quantify one thing. I've got you to quantify your thoughts. And I wonder, have you actually ever thought about your thoughts? Like, what even is a thought? And what are your thoughts made up of? So thoughts are generated in the brain, which are composed of 100 billion neurons that transmit impulses through synapses. So thoughts are electrochemical reactions. And this is a biological neuron. And how a biological neuron works is it takes in stimulus. Once it has enough stimulus, it then sends the signal onto the next neuron. And in 1957, Frank Rosenblatt created the first artificial neuron, and he called it the perceptron. Now, the perceptron was based and is based on how a biological neuron functions. So let's go about comparing the biological neuron and the artificial neuron. Well, they both do the same thing. They take an input, they process it, and they produce an output. The only difference between a biological and artificial neuron is the process. Instead of a process being a biological one, in the artificial neuron, it is a mathematical equation. And this simple yet beautiful mathematical equation encapsulates a lot of the biological neuron's functions. And we're going to just look into this. So the inputs, X, get multiplied by the weights. And what are the weights? Well, the weights are the strength of the bond. They actually put a value on that. And what do I mean? Well, Donald Hebb is a psychologist and is actually the father of machine learning. Yes, the father of machine learning is not a computer scientist. It is actually a psychologist. And he came up with the phrase, neurons that fire together, wire together. In other words, the more the neurons get fired in your brain, the stronger that bond is between them. And we can see this in everyday life. If I was to go from here to my second home in Buckingham Palace, initially I would take and use Google Maps to help me get there. However, the more I keep doing this route, the less and less need I have for Google Maps. And this is the same with your brain. The more these neurons get fired, the stronger the bond becomes, and therefore it's easier and the strength is built. So going back to what a weight is, well, weights are actually putting a value on this strength. So weights that are close to zero have a really weak bond between each other, whereas weights that are around and larger than 1 have a very strong strong connection with each other. So weights are just putting a number on what we observe in the biological function. Now we've got the bias. And the bias going back to is quantifying that threshold. So going back to the biological neuron, once that threshold is reached, it then sends a signal on. Well, B is actually quantifying that value. It's saying once B, this number is reached, send the signal on. And how it goes about sending the signal on is it's the activation function. The activation basically encapsulates all of the weights and biases and basically tells the function what to do. And you can see this in this graph. Once the bias is reached, that threshold is reached, the activation function comes along and tells the signal to be passed on to the next artificial neuron. Also in Hebb's research, he stated that he discovered that every experience, whether it's sight, smell, touch, triggers thousands of neurons, which form neural networks. And this is what he used to explain the brain. And artificial neural networks are, again, based on the brain. We have, sorry, I think people are wanting to come in, so I'm just going to admit that. So artificial neural networks are one way that a machine thinks and learns. And as you can see, that this is essentially a group of artificial neurons or perceptrons. And this is how they work. So let's compare how you think and a machine thinks in identifying whether it's observed a cat or a dog. On the left, this is how you are thinking. These electrochemical signals get thrown through your brain, through these neural networks, and you identify whether you have observed a cat or a dog. However, on the right, we have how a machine learns and thinks. And as you can see, the inputs get sent in, the artificial connections get triggered, and then it's able to identify whether we have observed a cat or a dog. So you can see the similarities between how you think and how a machine actually goes about thinking. So this is the fundamentals. So we're going to take a step back and actually look at what is machine learning. So in traditional computing, you tell the computer what to do. So you say to the computer, do this, do that, and the computer does it. Whereas in machine learning, the machine learns the pattern rather than you explicitly telling the machine the pattern. So in other words, let's take this back to a food analogy. In traditional computing, you give the computer the recipe. You say, do this, do that, and the computer follows the recipe. Whereas in machine learning, you tell the computer, here's some ingredients. I don't know, some chicken, cucumber, onions, and you come up with a recipe that meets some aims. Some aims that it tastes good and that it's healthy. And what the computer does is it will cook up these ingredients multiple times until it makes a recipe that is healthy and it tastes good. And now, you can see some flaws with this. If I was to give a machine moldy bread and moldy butter and asked it to make the aims and meets the aims that it tastes good and is healthy, the machine will try to do that, and it will keep cooking up moldy butter and moldy bread until it tries, and it will try and meet these aims. And this leads to the thing, if you have junk into your machine learning, you will get junk out, you will get a bad model. But we'll get onto that later when we talk about the challenges faced in machine learning. So let's look at how machines actually learn. Well, similarly to humans, humans actually do learn in different ways. Here we've got two examples. One, which you may remember, you may have had a parent or guardian who was able to teach you things such as riding a bike. However, there are also times when you were left by your own devices to learn things about the world around us. And this is the same with machines. Machine learning can be broken down into two key areas: supervised learning and unsupervised learning. Supervised learning is where you actually tell the computer what to learn. So going back to the cat and dog analogy, you say, this is a cat and this is a dog. While in unsupervised learning, you don't actually tell the computer what to learn. So you give it a load of cat and dog images and you say, you come up with a classification. You tell it, and the computer will try and classify this into a cat and a dog. Going back to the food analogy, and again, sorry, I realize this is probably a key time people are eating, but supervised learning is when you give the computer the ingredients and the final dish, and then you tell it to find a recipe. So here on the left, we have a Thai green curry. So you would give the computer the ingredients for this Thai green curry, and you would say, this is what I want to replicate. And the computer will literally try various recipes until it is able to recreate that dish. Whereas in unsupervised learning, you say to the computer, here's some ingredients. and you ask it to create a new recipe and a new dish. So you just give computer these ingredients, and the computer will keep coming up, but obviously it has to make some aids that is edible and it tastes good, but it will come up with a new curry, for example, that we haven't been aware of. So these are the two types of machine learning. And let's again go back to a classification task to explain this. So you have the dog and the cat. In supervised learning, you have what is called labeled data. Again, the cat with pointy ears is labeled a cat, and the dog with the round face is a dog. And we tell the computer this. However, in unsupervised learning, we give the computer unlabeled data. So we tell the computer, here are a load of cat and dog images, and we hope that the computer learns that pointy ears is a cat and a round face is a dog. And that is how they learn. Either way, both unsupervised and supervised learning use neural networks to get it to learn the data. And just as much, I'd just like to make a disclaimer. I know it says unsupervised learning, but there is supervision required from us machine learning engineers because we need to check that it's created something good and edible. The proof is in the pudding. Just as much as with cooking, if it tastes rubbish, you don't want to serve it. And that's the same with machine learning. If we've got something that tastes disgusting, we don't want to release this into society. So, okay, this is all great. This is a neural network, but how do they actually go about learning the data? How do I get from this data, and how does it actually learn what a cat and a dog is? Well, like humans, neural networks learn by their mistakes, but we just call it optimization. So this is actually a machine learning pipeline. So you take data, you do data prep, you evaluate a loss function, and you minimize the loss function, and it goes. And the first step, we're going to break this down. We're going to look at all of these in each step. So the first one, let's look at the data. Going back to the food analogy, the data comes in as raw ingredients. So this could be anything from social media to, I don't know, the finances you have. So got raw ingredients, and we can't just send these raw ingredients. Just as much as you can't cook with onions with skin on and carrots with the end still in, we need to do some data preparation. So we need to cut the vegetables, we need to do some cleaning, and we need to make sure the neural network is going to learn everything we need it to learn. After the data has been prepared, it then gets sent into the neural network, and the loss function is calculated. This is where optimization comes in. So the loss function is calculated, and then we minimize the loss function. And the parameters are then adjusted to find the minimum loss function. So let me explain. So the data comes in, then loss function is calculated. Optimizers come in to minimize the loss function by changing the parameters in this neural network. The data then gets sent back into the neural network, and a new loss function is calculated. The optimizers look at this loss function and then adjust the parameters in this neural network to accommodate the new loss function. The data then gets sent back in to the neural network. The loss function is then recalculated, and the process goes on and on again. So this is what we call a training loop. And this is how we get neural networks to learn. So let's go in a bit more detail. What is a loss function? Well, the loss function is the choice of error function, which is how the optimization algorithm is told how good the model is. Going back to a human analogy, the loss function is actually analogous to pain, and the neural network and the optimizers will do everything it can to minimize the pain. And the loss, as a machine learning engineer, it's your responsibility to choose the best function that best suits your problem. So for example, let's take these dots and this straight line. We just want to fit a straight line to these dots. As you can see at the moment, we have some extremely large errors. So this has a huge loss function. And in order to minimize that, we would just change the straight line or change the parameters in order to reduce these errors. This is an actual example of what is called the mean squared error, and this is a loss function that is used in logistic regression problems. But there are so many loss functions, and there are only 3 here on this slide to name a few. So mean squared logarithmic error and mean absolute error. There is so many more. And again, it depends what you want to do and the problem you're facing And as a machine learning engineer, it is your responsibility to choose that or come up with your own based on the problem you're trying to solve. Now, after the loss function is calculated, optimizers come in to change all the weights and biases in this neural network. So the weights and biases in this neural network can be sort of represented by all the connections between these neurons, and these get adjusted by these optimizers in order for the data to get sent back in and the loss function to be recalculated. And optimizers are responsible, also fancy ones, for changing the learning rate. So going back to sort of a pain, just as much as humans have different rates of learning, so do machines. So just as much as when we touch a hot pan, we know never to touch it again. Those who are quick at learning. Those that aren't so quick at learning may need to touch this hot pan multiple times before they realize that this isn't a great idea. And this is actually defined by the learning rate. So just as much as humans have different learning rates, machines also have different learning rates. And this is a parameter we as machine learning engineers can adjust, and fancy optimizers will actually adjust it for you, so you don't need to worry about it. But essentially, they will change weights biases to minimize the pain and minimize the loss function. Now, all of this can be encapsulated by this mathematical equation. And please don't get bogged down by the maths. Everything I've just said is basically, as I said, encapsulated by this equation. But we'll just quickly go through. So these are the new weights and biases in our neural network, and they are calculated using what is currently in our neural network and subtracting the learning rate and taking the gradient, so the change of the loss function. And this is, again, the loss function is predefined by the machine learning engineer, but this equation determines how this machine is actually going to learn. And in summary, this is how a neural network learns. And in order for a neural network to learn, the neural network architecture may need to be adjusted. Now, what do I mean by that? Well, you may need to vary the width of the neural network. So for example, here in my layers, I've only got a layer of 3 neurons, and I've also got a layer of 5 neurons. You may also need to vary the width of the neural network. So you may need to add more layers, and this is what we would call deep learning. You may have heard of deep learning, as this has hit headlines multiple times. And all it is it's defined as a neural network with many layers. And it's up to the machine learning engineer to adjust these neural network architectures so the machine learns. So basically, this is what we call hyperparameter tuning, and we may need to vary the width of these layers, the depth of these layers, the learning rate, all of these things in order to get our machine learning how we want it to learn. Now, in the modern era, we have lots of different data types, whether this is text, images, and audio. And as a result, this has led to an explosion of different neural networks. Because remember, the neural networks take the design of the data provided. And if we've got different data, we've got different designs. So instead of keeping up with the Kardashians, we are now keeping up with the neural networks. And here are just a few. Here we've got recurrent neural networks, deep sets, transformers, graph neural networks, multi-layered perceptrons, convolutional neural networks. These are just a few of the neural networks that are working on different data types in order to try and learn these different data types. And to give you an example of what machine learning is being actually used on your social media platforms, here we have Instagram, and you will have a convolutional neural network looking at your images. So convolutional neural networks look on image data and video data, and they will be making sure that you aren't posting anything that is disrespectful, hateful, and inappropriate. You will then have a transformer, and transformers work on text data. The most famous transformer, I think you may have heard of it, is ChatGPT. And these transformers work on text, and they may look at you searching, I don't know, in Instagram for, I don't know, Skims, which is one of Kim Kardashian's company, and then it will then start advertising to you using that company. Well, this is a transformer that's been able to use your search to then make predictions and help with advertisement. Then you've got a graph neural network, and a graph neural network will be going into your followers and going, oh, you know so-and-so, oh, you may be interested in knowing this person, and you may want to be friends with this person. This is what is a graph neural network being used. Now I can hear you saying, please tell me more. This is so interesting. So we're going to actually look at convolutional neural networks, and convolutional neural networks are used on image data and video data. And a convolutional neural network is an artificial neural network that features one or more convolutional layers. So before we get into how machines process information, let's go back into how humans process visual information. So again, this is where you can write something in the chat if you don't. I've seen people in the chat, thank you. But like, again, did you know that it takes your brain 100 milliseconds to process an image? True or false? So again, feel free to write your answer in the chat. It will be great to have some interaction, but if not, just think about this, because this is basically how long it takes from you looking at this image of a dog to your brain going, thank you, Bill, true, and to actually you identifying it as a cat or a dog. Brilliant, we've got loads. Thank you very much. So, well done, Dave. It's actually false. It actually takes only 13 milliseconds, and a team of neuroscientists from MIT have found that the human brain can process an entire image that the eye sees for as little as 30 milliseconds. So it's very quick. Your brain can process images extremely quickly. And how does it go about processing it? How does it go from the eyes to actually processing what it sees in the brain? Well, it does this by the visual cortex, and the visual cortex is the primary visual cortex is the first bit of processing your visual information. Now you're like, how do we know about this? Well, in the 1950s at Johns Hopkins University, David Huber and Thorsten Wiesel performed pioneering research on how visual information is processed in the brain of mammals. And this is just a photo of them at their laboratory, and they actually won the Nobel Prize for their work in 1981. And what was their experiment? Well, they had a cat asleep, and they put electrodes in the primary visual cortex of this cat to measure the specific neurons in that cat's brain. They then put some stimulus on the projector and watched how the neurons were fired in that cat's brain. And what did they conclude? They concluded that the cat's primary visual cortex neurons were only stimulated by certain angles or orientations. So specifically, we had on this graph, I hope you see my mouse. So this is just a graph, and this graph shows that at a horizontal line, just on the projector, there is no stimulation. So this neuron isn't firing. However, at a vertical a vertical line, there is a lot of stimulation experienced in this neuron. So they concluded that how a brain processes visual information is by breaking down an image. So so when you see something with your eyes, this gets sent into the primary visual cortex, and the first neurons that look at this image actually break the image down into just line orientations. They don't actually see the actual image in its entirety. So say, for example, me looking at this laptop, it would actually just see sort of a rectangle or lines in different orientations. And then this gets sent on to more and more complex neurons that are able to form the curves of the laptop, the keys of the laptop, and other things that we observe. So the idea led to the sort of terminology of simple neurons that get led into more complex neurons, which form the images that we see. And neocognition is the first convolutional neural network architecture, and it uses this idea of breaking images down, which we'll come on to in the next slide. But in 1988, neocognition was the first neural network which was able to categorize handwritten digits. And what I mean is the convolutional layers, and this is why it's called a convolutional neural network, is a convolutional neural network is comprised of convolutional layers and then a neural network. And these convolutional layers break the images down. So take, for example, an image of a cat. It will go through so different convolutional layers will pick up different orientations of lines in that image, and it will build that picture up, and then that gets sent into the neural network. So the neural network doesn't actually see the original cat image. It goes through these convolutional layers and it sees the output of these convolutional layers. So this is where the idea of the sort of simple neurons getting put into more complex neurons comes in. It goes through the simple convolutional layers and breaks down the image and then gets sent into a neural network. And this is actually one of the most famous convolutional neural networks. It's called LeNet-5, and it was designed by LeCun et al. In 1998. And this was actually used in the postal service. So this is why machines are rerouting your post, sending your post to the right place. And this is the neural network that is doing that for you. Now, as you may be aware, neural networks aren't perfect because sometimes your post ends up in the wrong place. And the limitations of convolutional neural networks do become evident when they're used to moderate content on social media. It doesn't completely block or remove the content. And why doesn't it? Well, ImageNet is a publicly released dataset containing 40 million labeled images and is used in classification, so whether it's a cat or a dog, problems, or object detection, so whether there is a cat in the image or a dog in the image, or none. But this data set is huge and it contains lots of random things from car objects to animals to household objects to, yeah, it's just a very random data set. But there has been research done that shows that CNNs struggle with different lighting, extreme angles, and different parts of the object. And what I mean by this is if it sees half a car, it will struggle in identifying that this is a car. So there are huge problems with getting CNNs to try and, which is a convolutional neural network, sorry, I've used the abbreviation there, CNNs to actually learn these the actual objects rather than just the pixels, which is what it's familiar with. And this leads on to sort of a fundamental thing. Machine learning is not about thinking like a human. Yes, the origins of machine learning were in how a human thinks, but at its fundamental core, machine learning isn't like mimicking what a human does. And as I said, by default, it isn't like human thinking, just the process of going about it. And secondly, we don't even want to mimic human thinking because humans have faulty thinking. We're not perfect, and therefore, why do we want to mimic that? But also machines aren't perfect. And we see this in the news and it hits headlines many, many times. So here are some articles just to show you a few of where we've encountered problems in machine learning and the challenges we face. So Google's algorithm actually showed job ads to men rather than women. Amazon actually had a data set and used a recruiting AI which showed bias against women, and that was because they had previously trained it on data sets and it was a mainly male data set because that's who had applied for their jobs. So they didn't intentionally do it, but by just showing them just training it on previous data sets, they had induced bias by accident. Then Apple also got investigated because both a husband and wife tried applying for a credit card. They both had the same income and assets, but the wife got refused the credit card, but the husband didn't. So this then got investigated. So you can see where there are huge problems. And this is how is bias induced. Sorry. So how is bias actually going about introduced into the data set? Sorry about that. So bias can be ejected into the machine learning pipeline at various stages. So going back to the machine learning pipeline, which we introduced at the beginning of this lecture, the problem can occur at any stage, including how the problem is framed. So for this section of the talk, we're actually going to pretend that you're machine learning engineers, and let's predict whether England will win the Euros 2024. But how are we going to do this? Well, the aim is we're going to decide that the total number of goals is our aim. We're going to say that if England score a lot of goals, then they're going to win the Euro 2024. Now, you would all automatically throw to me and say, wow, Susanna, that's not necessarily true, and which I would agree. So even how we framed this problem, I've introduced a bias. Now, we can introduce bias into the data. So here we've got certain data, and these are the data I have on Harry Kane and all the other players. I've got number of goal scores, height, hair color, hobbies, number of red cards, and goals. So as you can see, these are actually the data I have available to me. But there are some data that you think would be useful, such as how fast they can run, which would actually be very useful to know about, but I haven't included. So even with the data I've got, I've automatically induced a bias into this machine learning algorithm. Not only that, I've data preparation. I have decided that hobbies and hair color shouldn't have an impact on whether Harry Kane could score. Now, that is a very fair and logical reason. However, I could get a machine learning on all the players' hair colors and whether their hobbies and try and find a relationship between that and whether they're going to predict whether they're going to score lots of goals. So as you can see, even how a machine learning engineer chooses what it's going to train a neural network on, actually it can introduce biases and introduce biases into this into the machine learning algorithm. And put simply, if you give a machine junky data, you're going to get a junky machine learning model. So junk in equals junk out. Going back to the moldy bread, if you give a machine moldy bread and moldy butter, it just can't help but create something disgusting, even if you make it aims that it tastes good and it's healthy. Now, what is the machine learning community actually doing to address these problems? Okay, we're aware there are biases, and biases can be introduced into any section of the pipeline. But, unfortunately, machine learning biases are hard to fix. First of all, it's not actually very obvious. So going back to the sexist AI tool that Amazon used, so they realized it was sexist against women and that they had trained it on a majority male data set. So they changed that and they added more women, and also they started getting it to ignore explicitly gendered words like woman. But then the system started picking up implicitly gendered words, such as executed and captured, which were more likely going to be in male applications rather than female applications. So the neural network architecture still picked up this gender bias. So as you can see, it's not an easy problem to solve. Second of all, the machine learning pipeline and the standard machine learning process is an imperfect process. Currently, a standard machine learning engineer will take data and split that data as the following: 80% to training and 20% to testing. So 80% of that the neural network will get trained on, and 20% it will get tested on. Now, if there is a bias in that data, as you can see, I'm going to train it on biased data and get it learning biased data, and then I'm going to test it on biased data, and that bias will remain in there. So at the moment, sort of the standard way of doing machine learning in itself is an imperfect process, and it doesn't help reduce bias in the machine learning models. Thirdly, another problem is lack of social context. So what does getting rid of bias look like? And different algorithms will work in different social contexts. So for example, take India and the United Kingdom. Both are different cultures, they have different values and different ideas of fairness. Therefore, if I was to take a machine learning model that had been trained on UK data and transpose it to somewhere in India, it just wouldn't work because just the whole culture is completely different. So as a machine learning engineer, you need to be very aware in which your machine learning model is actually going to be applied in. And finally, the definitions of fairness. So what is fairness? Let's go back to the philosophical question. How would we go about defining fairness? Going back to the credit card example in Apple, is 50% of women and 50% of men considered high risk, or is everyone considered high risk? What does fairness actually look like? And as machine learning engineers, I think we're looking to philosophy to try and help us with that. And there are attempts to get fairness integrated into our models, just simply by showing, making sure that you've got a good diversity in your training data set. And as I said, it is up to us as machine learning engineers to be aware of the biases and do everything we can to mitigate it. Yes, we can't we are aware of them, but we can do simple steps by just making sure the machine sees a diversity of genders, races, and religions, for example, and so it is well diverse in picking that up, and it doesn't learn those things. So put simply, maybe you could be the solution. I'm sure that we are calling for a diversity of people in machine learning because you all have different backgrounds, different perspectives, and different ideas, and we need this. And hopefully there's someone out there who can be able to look at these problems and address them. So we need you to come in and fix these problems. And for the final bit of this talk, I'm just going to look at how are neural networks being used in astronomy. As I've said, I am an astrophysicist and I'm so excited about astronomy. So we're going to end and land this talk on how it's being used in astronomy. So we have lots of data in astronomy. I'm working on gravitational waves, and that is a gravitational wave detector on the bottom right, and we have lots of data. We have data from various telescopes across the globe, including the Square Kilometre Array, and we also have what is the Vera Rubin Observatory, which is going to be proposed. So again, would love some audience participation. How many galaxies are we expected to discover with the Vera Rubin Observatory? This is going to take the entire images of the entire night sky every 3 days. So A, 16 million, B, 1 billion, and C, 20 billion. Oh, you are very clever. It is C. Yes, it is C. We're expected to observe 20 billion galaxies. And this is just a nightmare for the average astronomer. It's just too much data. We don't even know how to go about it. And this is a problem we're facing in astronomy. We have too much data. However, research in 2023 showed that a neural network with human supervision could go through 11 million images to identify 527 new strong lensing candidates. And strong lensing was originally predicted by Einstein's theory of general relativity and is a rare event where light bends around heavy objects such as galaxies. So here you have a galaxy in the middle, so we call the gravitational lens. This is the middle galaxy. The blue bit is from actually a distant galaxy, and light from this distant galaxy is getting bent around the middle galaxy, and we observe this sort of horseshoe on Earth. Neural networks have also been used to identify 301 exoplanets. So they have been used to go through Kepler data, and Kepler's looking at various light from stars and neural networks have been used to identify these exoplanets, hopefully leading to, possibly maybe there's life on Earth, but also, is there any new physics that we're missing, and what are the physics going on these other planets? But it's not just processing the data quickly. Neural networks are actually challenging some of our theories of galaxy evolution by classifying the galaxies differently. So in this research, the computer was given a load of galaxy images and it's unsupervised learning. So it was left to its own devices to classify them. Now, the machine came up with a different classification to how humans have originally classified galaxies. So the researchers were like, have we misunderstood this new bit? Have we misunderstood galaxy evolution? And is there any physics we are missing? So as you can see, this is such a new field. And this is also the research I'm doing. So I'm going to just briefly touch on what I'm doing. So I'm part of the LIGO scientific collaboration, and we're part of a group of scientists trying to learn more about the universe from gravitational waves. And I'm specifically trying to speed up the gravitational wave data analysis pipeline using my multi-layered perceptron or neural network called Learning Match. And this neural network is used to predict the match. So what is a gravitational wave? Gravitational waves are ripples in the curvature of space-time produced by accelerating masses, such as two black holes or two neutron stars colliding. So here in this animation, we have two neutron stars orbiting each other, and they're releasing energy in the form of gravitational waves. As a result, their orbit gets smaller and smaller till eventually they collide, and this burst of energy gets sent into the universe and eventually gets detected by one of our detectors across the globe. We have two in America, one in Japan, and one in Italy. And we hope to learn more about the neutron stars and black holes these gravitational waves originated from in order to learn more about our universe. Now, searching for gravitational waves in our data is extremely expensive because our data is very, very noisy, as seen by the blue, but our signal is very, very weak, as seen by the pink signal. So we really want to use neural networks to speed up the process. Now, the aim of my project, and I'm not going to get into the sort of basics of this because I'm running out of time, but essentially I'm trying to replace this mathematical equation and get it learning the relationship between the parameters of the neutron stars and what is defined as the match, and replace it with a neural network. So I'm going to just sort of end on what have I learned as a machine learning engineer. Firstly, we are looking into the unknown. Well, I need a neural network to be accurate within 1%, which hasn't been done before. And therefore, I was looking to the machine learning community for answers, but actually a lot of the problems we're facing in astronomy, the machine learning community actually hasn't done yet. So we're actually in the darkness ourselves. Second of all, it can be misleading. What has the neural network architecture learned? In my machine and in my PhD, I have thought my machine has learned so many times, and actually when it's come to it, it hasn't actually learned what I've needed it to learn. And when I've applied it, it showed errors. Therefore, it's very misleading. Finally, it's extremely frustrating. You are really looking for a needle in a haystack. To try and get your machine to learn is like you're tuning all these parameters to try and get it to learn, which is why, in my opinion, machine learning engineers are paid nice salaries. So this is a summary of what neural networks are currently being done and used in astronomy, but there is still so much research, and who knows what the future looks like. But this is where we need your help. We have lots of projects on zooniverse.org, which we need you to get involved with because we need your help. Just as much as computers are imperfect, we actually believe the combination of humans and computers combined can actually help in solving some of the huge problems we face in astronomy. There are other projects on zooniverse.org, so biology, history, English, if that's more your thing. But I'm, again, an astrophysicist, so I'm going to point you to the astrophysics problems. So black hole hunters, galaxy zoo, planet hunters, gravity spy, dark energy explorers are all the projects that we would love you to get involved with, and we need your help. One of them, again, I'm going to just highlight what you're going to be doing is kilonova seekers. So we have a telescope in La Palma called GOTO, and it is looking and taking images of the night sky, looking for explosions. These explosions can be from two neutron stars colliding, supernovas, which is when a star dies and release a bright explosion, or just stars changing their brightness. And in this research, a convolutional neural network has gone through a load of data and is unsure whether it's observed. So it will classify it into three things. It's seen an explosion, it has not seen an explosion, or it's uncertain. And actually in this, you will be looking at data which this convolutional neural network has deemed uncertain. It's like, I don't know what I'm seeing in this image. And you as humans will come along and go, don't worry, you've seen an explosion, or don't worry, you've not seen an explosion. So this is where I believe machines and computers can actually unite and help each other in their imperfections. Just as much as a machine learning algorithm is imperfect, humans humans are also imperfect. We can sort of use our strengths to break and learn more about our universe. So I'm just going to wrap up and conclude on, are machines the next Einstein? Well, in some ways, I think they're better than Einstein. Could Einstein analyze 11 million images and to prove his own theory of general relativity in strong lensing? I really don't think so. But in some ways, Einstein is so much better than machines. Could machines come up with the next theory of general relativity, which would revolutionize how astronomy is done for the next 100 years and make incredible predictions that we would later observe? I really doubt that at the moment, but I'm not going to say never because who knows, the future lies ahead. So I'd like to thank you for listening, and if there are any questions, please do leave them in the chat and I'll have a look. If you would like to get involved in a Zooniverse project, again, we really need your help, so please go and check out the Zooniverse website and get involved with actual research. If you are interested or have any questions, please do go and contact me on my email address, Or I've also got Instagram and LinkedIn, and the link to my the YouTube channel I'm part of, which is called Field of View. And we research and basically want to show, as I said, anyone can do physics. So please do check us out. Anyway, thank you for listening. And are there any questions?